Let's talk about a world where a surgeon's incredible skill gets a major boost from the absolute, unwavering control of a machine. This isn't science fiction, it's the reality of surgical robotics. We're talking about a field that's all about bringing a whole new level of accuracy to procedures where perfection is the only option. It really is a partnership, right? You've got the surgeon's years of experience meeting a robot's rock-solid stability. And that collaboration, it doesn't just give doctors more control, it gives patients a much greater peace of mind. But how in the world do you actually build one of these things? Well, that's where things get tricky. Building the actual hardware, the robotic arms, the casings for the joints, that is a massive, massive manufacturing challenge. This is where a brilliant idea for a surgical robot crashes right into the hard reality of physics and material science. So the heart of the problem comes down to three things that are always fighting each other. First, you need components that are perfectly precise for alignment. Second, they have to be incredibly strong to handle all that motion. But third, they also have to be lightweight enough to move instantly and smoothly. Nailing that balance is, well, it's everything. And believe me, the stakes could not be higher. We're talking about surgical tools where even a microscopic error in a joint can lead to drift or stiffness right in the middle of an operation. Any kind of inconsistent movement is just not an option. So the manufacturing, it has to be absolutely flawless. Okay, so the team's first shot at creating these parts used a pretty common prototyping method, and the initial tests, they were a success. The parts actually worked. But this success was hiding a huge roadblock, one that made the entire project basically impossible to scale up. The problem wasn't the design, it was the process. The prototypes were made using CNC machining. That's where you take a solid block of metal and painstakingly cut each part out of it. Yeah, it's precise, but it is also incredibly slow, super expensive, and creates a ton of waste. Basically, the exact opposite of what you need for mass production. So, just how bad was this problem? Get this. The prototype parts were 5 times the target cost. Just let that sink in for a second. 5 times. At that price, manufacturing this robot at scale wasn't just going to be hard, it was literally impossible. The project had completely hit a wall. And this is the turning point in the whole story. The client, staring at this manufacturing dead end, didn't show up with a new design or a purchase order. They came with a question. A really fundamental engineering challenge that, it turns out, opened the door to a totally new way of thinking. Just 3 words: can we cast this? Now, casting, pouring molten metal into a mold, is a fantastic way to make parts quickly and affordably. But could it possibly deliver the insane level of precision and strength that a surgical robot demands? That was the million-dollar question. And this was not an easy thing to figure out. The engineering team had some serious concerns. Would a cast part actually hold its shape down to the micron? Could it possibly meet the intense strength and stiffness goals? And the big one, could they make this switch without a single tiny compromise on performance? So the answer wasn't a simple yes or no. It took a really deep engineering dive that led to this innovative, hybrid solution that would completely change the game for this project. The team was super methodical about it. First, they just broke down the design of every single joint and casing. Then they ran exhaustive computer simulations. We're talking stress, cooling, how the material would flow. It was only after they understood every single variable that they felt ready to propose a solution. And the solution was brilliant. It wasn't about using one type of casting. It was about combining 2 different, highly specialized methods into one single hybrid process, basically using each one for what it does best. So the first part of that solution was something called semi-solid casting. This process is absolutely perfect for creating parts with incredibly complex shapes while hitting that high-dimensional accuracy they needed for all those critical joint connections. And just like that, the precision problem was solved. The second half of the puzzle was squeeze casting. Now, this method forges the metal under immense pressure, which creates parts with a really dense, robust internal structure. They used this for all the structural zones that had to handle dynamic loads and stress. So, boom, there's your strength problem solved. But the innovation didn't stop there. It turns out, standard aluminum just wasn't going to cut it. It wasn't strong enough. So, the team had to evaluate and select specifically tailored alloys, materials that were engineered to give them that superior strength-to-weight ratio that perfectly matched the robot's needs. And with this amazing combination of hybrid processes and custom materials, the team was finally able to turn what was an unscalable prototype into a viable, castable product that was actually ready for volume production. So if you look at the journey, it started with a great concept, right? That was validated by a working prototype. But that prototype hit a dead end because of cost. Then came the brilliant hybrid casting solution, which completely broke through that wall. It created a scalable platform and a real path forward from just one working model to mass production. I think the ultimate takeaway here is pretty powerful. In a field like surgical robotics, precision isn't just an idea on a whiteboard. It has to be physically built into every single joint, every arm, and every single move. This story isn't just about building a better robot. It's a blueprint for how innovative manufacturing can solve what seem like impossible problems. It really makes you wonder, right? What other life-saving technologies are just one breakthrough process away from changing the world?